Precalc chapter 4.2. We're going to continue on. Now today we're going to talk about degrees and radians. So there's a little bit of switching. There's a little bit of different, like how can they break up degrees into a different format. How do you measure angles? So we'll start with that today. So these are all angles up here, guys. And what you see is that there are some things or some definitions, some highlights here of what these angles or what makes up an angle. And so what we have here is we always want to have an initial side of an angle. Okay? We also, that initial side is where we start. And when we rotate an angle, it's always counterclockwise. So going up to our terminal side. Terminal side is where you stop your angle. And they are connected at the vertex. So an angle, guys, is just a rotation about a vertex or a fixed point. Now, over here, they put that angle in what we call standard position. They anchor your x and y axes, leave the vertex at the origin, and your initial side will always be the positive x-axis. So that's the way you're facing every time you do this. And then you open counterclockwise to your terminal side. So you're always moving up. Not always moving up, but when we move up, as we have down here, we have a positive angle and a negative angle. So when we go to say, I am moving in a counterclockwise rotation, that is a positive angle. We could also move in a clockwise rotation going down. That is a negative angle. Okay? You can get to the same exact terminal point moving in a positive direction or in a negative direction. We're going to get that in a second. And on the very bottom of here, I do have the definition of a degree. Degrees, when I say, hey guys, turn 60 degrees, you guys are probably pretty familiar, or a 45 or a 30 degrees, because that's what we grew up on. We talk about degrees, even in our temperatures and everything. Not everything revolves around degrees. We're going to be talking about the radians soon enough. All of these, what an angle is, standard position, positive, negative, works for degrees and it works for radians. But a degree, guys, is just defined as 1/360th of a full rotation, counterclockwise, about the vertex or a fixed point. So that means when you take any particular circle, one rotation, and cut it into 360 equal pieces, each degree represents 1/360th of that circle. Kind of makes sense. So if you've gone 60 degrees, you've gone 1/6 of the circle. Okay? Any questions on this stuff? I think most of it is stuff that we've seen before. Kind of makes sense. The next one, a little wordy on top there. It says that a degree measure can also be expressed using a decimal degree form. The decimal degree form is this one, 213.875 degrees, or 213 and 875 thousandths of a degree. So obviously, more decimal places you go, the more accurate things are. Or we can use a degree minute second, the DMS form, where each degree is subdivided into 60 minutes, and each minute is subdivided into 60 seconds. So what we're going to do today is we are going to switch from one form to the other, back and forth. That's our first job today. And we need to convert any DMS and decimal degree forms. So let's do that. The first one's in the degree form. I need to switch it to the degrees, minutes, seconds. So this, how you read this one is 89 degrees, 56 minutes, 7 seconds. Okay. So how do I switch between these? Well, first of all, 213 is a nice whole number. That's how many full degrees you would go. So that's pretty easy. I can say, hey, that's 213 degrees. The way we're going to handle the second part, that decimal, is if you look above, it says it's subdivided into 60 minutes. So what you need to do is say, hey, how many minutes are going to be used of 0.875? 0.875 minutes. So I'm going to, okay, we got our degrees. I'm now going to take 0.875 and multiply it by 60 minutes per degree. Because when we do this, then we can subdivide it into minutes. So that's not miles, it's minutes. We'll put MIN. Now, up above, it might be harder to see on this screen. Minutes, guys, has this little mark right here. Right there. Seconds has this mark over here. I'll draw it a little bit bigger. So if I said I wanted minutes, I just put apostrophe. Is it apostrophe above? And if I'm talking about seconds, it's two of them. It looks like a quotation mark in a way. So sometimes they don't use minutes and degrees in words. They actually might instead just do this. Minutes over degrees instead. So they would put the little mark of a minute because that's what they're going to use. So what if I take my calculator out, take 8.75, times it by 60, what's the leftovers, or what number do I get? Because I'm assuming there's going to be some kind of whole number component to it and some kind of decimal. And that's what we're going for. So minutes equal, someone give me that decimal. What do we got? Okay, everybody just took out a calculator, or at least half of you. Tell me the number. What's 0.875 times 60? 52.5. So that's 52.5 minutes. Well, I don't like this as in 52.5 because it's supposed to be out of 60. So therefore, I'm going to say that's 52 minutes. So right now, we have a number of 213 degrees, 52 minutes. How do you think I get the seconds? Now hold on.
Oh, because that's the seconds, so it's going to be 30
There we
seconds.
go. Now I got to convert it down to seconds. So I take the decimal that I had here and multiply that by 0.5 minutes times 60 seconds over 1 minute will equal 30 seconds. So your number is, instead of going 213.875 degrees, you're going to go 213 degrees, 52 minutes, 30 seconds. Have you guys ever seen that before? You guys ever seen that on maps about the globe? Coordinates? You may have seen it in some movies sometimes. You watch, I know, like action movies, or they start giving coordinates of where am I located on the globe? You can do this. This is how you do that. They use this to say, okay, 213 this way, 52 minutes, 30 degrees latitude, that type of thing, and longitude. So it's pretty cool. So using that knowledge, I mean, it seems pretty easy, right? You take your whole number, write that down, that's degrees. Your minutes, multiply your decimal by 60, take that whole number, that's your minutes. And then you take the leftovers again, that decimal again, multiply by that by 60, and that becomes your seconds. Make sure to put the little tick mark, the apostrophe, and then the double apostrophe for minutes and seconds. Now, if I had to work my way the other way, how can we go about doing that one? So yeah, we're going to divide by 60s. But here's the thing. 89 is 89. So I think everybody should be okay with that. So what about the minutes, though? So 89 point something is what it's going to end up being. Well, in the large scheme of things, to get to that 56, the first time around, I multiplied by 60 the first time, right? So this time I need to take 56 and divide it by 60. But to get to the 7, or in our case the 30, I did what again? You multiplied by another 60, right? That was 2 60s. So what do I have to do with the 7? I need to take the 7, and I actually not going to divide it by one of the 60s. I need to divide it by the 60 again, or 2 60s, or 60 times 60. So 3,600. Because how many seconds are in an hour? Think of 89 as your hours. 56 is out of minutes. There's 60 minutes in an hour. And 7 seconds out of an hour would be 7 out of 360. And what you're going to do then is take your calculator out, divide them, figure out your decimals, and add it all together. What is 56 divided by 60? 0.93 plus 7 divided by 3,600.
0.0019.
And when you guys put those all together, 89.9319. Now you're back to same all degrees. So it's actually not too bad going from one direction to the other. Either I'm multiplying by 60 every time, or just dividing by 60. Any questions on that?
Do you want us to take like 2 from each?
Now, when I just looked at the answer they got, guys, was 89.935. And how the heck did they get 935? First of all, look at the directions. I forgot to read that last part. It says to the nearest thousandth. So, if I think about that, that's tenths, hundredths, thousandths. Oh, shouldn't that just be a 2? It's interesting. So why do they get a larger number?
Couldn't you divide the 7 seconds by 60 and then put that as a decimal, like so 56, and then divide that by 60?
0.0019 would be rounded.
So we found that we rounded when this should have been 0.333. And if that's 0.333, right, because the 3 won't kick the next one up, now when you add those across, what do we get? Because it's not going to be this. Now it's going to be 0.934. And then, actually I got to go the other way now, right? So that'd be a 12 and a 5. And now if I round that number to the nearest thousandths, I get what the book says we should have. So, okay, lesson learned. When it says round to the nearest thousandths, if it's got a repeating decimal, you need to go out to that point where that decimal should be. So in this case, 4 places, thousandths. So, most of the time, degrees work okay in the real world, but there are times the relationships, they're not going to work out very nicely or seamlessly. Degrees is something we made up. We decided, take a circle, divide it by 360, like I said. Radians, though, happen to be a pretty natural occurrence. They find this just by taking a circle and dividing it, and we're going to see here in a second, that they've actually found this thousands of years ago. They didn't have it to the accuracy that we have today, but using 3.14 for pi, which is radians, is really accurate, and you can build a lot of things, buildings and things like that, with just those three numbers. So the measure of theta in radians of the central angle, remember central angle is the angle at the center to an intercepting arc, is equal to the ratio of the length of the intercepted arc to the radius of the circle. So, if you took some arc S and divide it by its radius, you will end up with theta. Central angle is a measure of 1 radian is intercept the arc with the same length. So if you take the radius of a circle and lay it across its side, so if we had a circle with a radius of r and an arc length of r divided by r is 1. That would be considered 1 radius. Or 1 radius. 1 radian. So radians, if you think about this, if you think about your circle circumference is 2 pi r. And if I divide that by 2 pi r, you find out that there are 2 pi radians in a whole entire circle. And remember, pi is 3.14, and so 2 times 3.14 is about 6.28. So in a full rotation, there's about 6.28 and some change in there radians, which is different than 360 degrees. We will have to use both, get used to both. There are some things here. Central angle represents 1 full rotation. So if you divide 2 pi r by r, you get 2 pi, like I just said. We got common ones there. You got 2 pi on the bottom. That's a full circle. You get pi radians. Pi radians is half a circle. Pi over 2 is a quarter of a circle. And pi over 3 is a sixth of a circle. So those are things that we're going to eventually figure out. We're going to remember those and be quick to recognize, especially when we talk about quarters, halves, and sixths. One that's not up there, I see, is an eighth. Because an eighth of a circle is pi over 4. So pi over 4 is another important one, 45 degrees. So what you guys probably want to know is, how do I switch again from degrees to radians and radians to degrees? The key is pi is equal to how many degrees? How many degrees are pi? Half a circle. Pi radians equals 180 degrees. And if you can remember that conversion, then you can use dimensional analysis. Basically, cancel your units. And that's what it's showing us here. That if I want to convert a degree measure to radians, I will multiply by the radians on top, degrees on the bottom. So pi divided by 180. That way your degrees will cancel, leaving you with radians. If I want to convert from radians to degrees, I will put degrees on top, radians on the bottom, so they cancel out. Pretty straightforward. You can use a calculator for some of these. Some of those you shouldn't have to use a calculator. Some of these you might even remember already. So if I want to convert 210 to radians, I take 210 degrees and multiply. Wait a minute, degrees are on top. I want to cancel them. So I need to put degrees on the bottom. And pi radians on top. And then just multiply. The cool thing about this is, what happens with our numbers? What can we do? divide, reduce, right? Technically, I could cancel out a 0 right away. What else can I divide that number by? Top and bottom? 3. So that'd be 7 pi over 6. Now, notice that I left it at 7 pi over 6. Look at part C and D. Do they even tell you it's radians? Part A and B, they have degree symbols on there. But when you are talking about radians, a lot of times they just leave off rad. Rad for radians. They could put radians there, you could put rad, you could leave it blank. As in, you don't need units, because anytime you see a pi, you almost always assume you're in radians unless you see a degrees. If you see a degree symbol, then you know you're in degrees. If you don't, you have to say, I am in radians. It's implied. I think you guys can handle negative 60. You just know that you're going to have a negative answer. What about 4 pi over 3? I want to switch that to degrees. So 4 pi over 3, which is a radian. So if you need to, put radians on top. Multiply it by pi radians on the bottom to 180 degrees on top. Radians cancel. Ooh, pi's cancel. And now I can do 4 times 180 divided by 3. Or, what's 180 divided by 3? What's 180 divided by 3? 60. And what's 60 times 4? 240 degrees. So we can do it that way. Another trick you guys can do here, if I'm switching from radians to degrees, take out pi, switch it with 180. 4 times 180 divided by 3 is what you just did anyways. So that's one way we can handle that as well. Now, when I talked about on that thing, I don't know if it's the first slide or the second slide, I said that, hey, if I took a positive approach or a negative approach on angles, I could still end up in the same spots. And that is because there are something we call coterminal angles. Coterminal angles are angles that terminate in the same place. AKA, they have a same terminal side. It doesn't matter if I'm coming from the same side or from the other side, okay? It doesn't matter, positive, negative. I could technically rotate past an angle and then rotate right back to it. Think of doing a 360. If everybody right now stood up, did a 360, and I went and I turned my back and said, okay, everybody do a 360, and turn around again, would I even know you guys did a 360? Other than maybe hearing some of you guys fall over. No. If I asked you guys to do a 720, you guys just twirl around 2 times, you're still standing in the exact same spot. So therefore, you started and stopped at the exact same spot, which, well, the starting part doesn't matter. But if you end in the exact same place, you have coterminal locations or coterminal angles. And so you can have multiples, actually an infinite amount of coterminal angles. And so, if you're in degrees, all you have to do is just add multiples of 360. Now notice that it says a plus 360 n. N is an integer. That's positive or negative. Or it could be 0, right? So any multiple, that means I can add 360, add 720, add 1080. I could subtract 360, I could subtract 720, and I could subtract 1080. Or I can add 0. And if I add 0, it's one angle. If I add 360, it's another angle. So every angle, I can go in the forward way or the backwards way to find a coterminal angle. Radians, on the other hand, same thing. I'm just going to add 2n pi, they call it. I think last year we may have actually used a k, 2k pi, if you remember that one. It's the same thing. So I could add 2 pi, I could add 4 pi, I could add 6 pi, I could add 25 pi. But I can also subtract 2 pi, subtract 6 pi, subtract 10 pi. I could find another angle. And I can keep doing this, going around the circle over and over and over again, spinning, 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 landing in the exact same spot. So I'm not going to necessarily go with the degree one. I think that's fairly simple and easy to find. So we'll do one with the radian measure. Now it wants you to identify all coterminal angles first, aka leave it with n in it. That's number one. The second one says then find and draw one positive and one negative coterminal angle. So first, if I have 3 pi over 4, because we'll start with part B, isn't that just 3 pi over 4 plus 2 n pi? Those are all coterminal angles. You can find any one you want now. The second part says find a positive and a negative, and then it wants you to draw it. Ooh. That's something we haven't done before. Actually, we should have done that maybe on the last slide too. So first of all, where's 3 pi over 4? How the heck do I draw that before I go and make it larger or smaller? Well, here's the cool thing. If I'm taking pi and cutting it in 4, remember pi is half the circle. So if I'm doing this, I'm actually taking pi and going 1, 2, 3, 4. 1, 2, 3, 4. I'm cutting it 2 pi into 8 pieces, or pi into 4 pieces, and then I can count 1, 2, 3. There I am. This is your angle right here. That's 3 pi over 4. Now, if I want to find a positive coterminal angle, I just need to add 2 pi to that. That's one option. Put n is 1. So what is 3/4 pi plus 2 pi? Well, first of all, that's just around the circle one more time. Boom, there I am. I'm in the exact same location. But what would it look like in terms of pi? The reason I skipped over degrees is because I can add 360 to negative 30. I'm fine. But how do I have to add these things? Can't just add those together. Is that just 6 pi over 4? Is it 5 pi over 4? What is it? I got 2 fractions, or I got 1 fraction plus another thing. How do I add things together? Got to have common denominator. The common denominator between 3/4 and 2 pi is 4. So to get this to have a common denominator, that's the biggest part, is I have to multiply by 4 over 4. 3/4 pi plus 2 times pi times 4 is 8 pi over 4. And what's 3 pi plus 8 pi? 11 pi. It's 11 pi over 4. Is that a positive angle? Yeah. Here's a cool thing. Watch this.
Where did you put
1. Yep. Go on.
Where did you put the n?
I chose n to be 1
Oh, okay.
to make it 2 pi.
Okay.
So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Look at that. I ended up in the exact same spot. I just counted 11 pi's over 4. Now, to get a negative coterminal angle, I'm going to... No, I don't like that. I'm going to subtract 2 pi. So now, I take 3/4 pi minus. Guys, we already did the groundwork. I'm not going to reinvent things. I'm just going to do this. Can I just use 8 pi over 4 right away? I don't see why not. That's 2 pi. And 3 minus 8? Negative 5 pi over, not 3, but 4. And guess what? If I go to graph that, I'll change colors here. 1, 2, 3, 4, 5. Guess where I landed? In the exact same spot. Homework for day 1, page 238, 1 through 25 odds. Have a great day.